Hello everyone, my name is Aryan and today I will discuss problems based on CR inequality. As I have already mentioned in my previous lecture, statement of CR inequality and proof of CR inequality. So now in this lecture we have a few problems and we will discuss about the solution of mentioned problem. So first problem is obtain the minimum variance bound estimator for mu in the normal population mu comma sigma square where sigma square is known. Okay, so this is our problem and come to the solution part. If x1 x2 xn is a random sample of size n from the normal population, then density function of normal distribution is, we can write it, x mu is equal to 1 upon sigma root 2 pi, this is comma, okay, 1 upon sigma root 2 pi exponential minus half x minus mu upon sigma square, okay, and the likelihood function L is joint density and we can write it product I going from 1 to n and density of x. So this is 1 upon sigma root 2 pi exponential minus half xi minus mu upon sigma square. Okay. So we can simplify this expression in form of next expression. So in next expression, now you can see here, this term and this term both are multiplied by n times. So that's why first term becomes 1 upon sigma root 2 pi to power n, and next term is what? Exponential minus half xi minus mu by sigma square. So this term multiply n times, so it's become exponential minus summation I going from 1 to n xi minus mu square upon 2 sigma square. Is it clear? So now you can simply see here, let's suppose we have first term is e to power x1 and second term is e to power x2 and we are multiplying these two terms. So you can write it e raised to power x1 plus x2, that means is equal to e to power summation of xi. So using this concept we are writing this one. Okay, is it clear? Okay, now next step is taking log of this equation. Okay, taking log both side of this equation, we get log L is equal to, this is first term and this is second term, that means log of this term into this term, and by log formula log A into B means log A plus log B. Okay, so first term is log 1 upon sigma root 2 pi to power n, and by log property we can write it n log 1 upon sigma root 2 pi. Is it clear? And second term is exponential and we are taking log of the exponential, then it's become free form exponential 1 upon 2 sigma square summation xi minus mu square. Is it clear? Okay, now let's consider first term is equal to k, where k is a constant, and independent of mu. Okay, and then we can write this equation in form of equation number 1. Log L is equal to k minus 1 upon 2 sigma square summation xi minus mu square. Okay, is it clear? Okay, so now again next step is just simply take, so next step, partially differentiating equation number 1 with respect to mu, we get del by del mu log L is equal to, first term is k and k is independent of mu, then it becomes 0, and second term is 1 upon 2 sigma square summation of xi minus mu square. So 1 upon sigma square, 2 sigma square is constant, and summation of xi minus mu square, that means 2 times xi minus mu, and differentiating mu with respect to mu it becomes minus 1. Okay, so now you can simplify it in form of summation of xi minus mu upon sigma square. Okay, then again we can take summation inside, summation of xi minus summation of mu upon sigma square. Then we can write next step, summation of xi minus this quantity becomes n mu upon sigma square, and we know that x bar is equal to summation of xi upon n. So we can write summation of xi is equal to nx bar and minus n mu upon sigma square. Then we can take n outside, it becomes x bar minus mu upon sigma square. Then del log L by del mu is equal to x bar minus mu upon sigma square by n. Okay, so this is our second equation. Okay, and we know that from Cramer Rao inequality, if the first derivative of likelihood function can be expressed in form of del log L by del theta is equal to t minus tau theta upon gamma theta, then minimum variance bound estimator t for tau theta exists. Okay, and in this expression, this is equation number star. In this equation, t is unbiased estimator for tau theta. Okay, so now you can compare equation number 2 with equation number star, and now you can see here in place of t what we have, x bar, and in place of tau theta what we have, mu. Okay, and in place of gamma theta what we have, sigma square by n. Okay, so that means in this, okay, so in this way we can conclude that x bar is minimum variance bound estimator for mu, and variance of x bar is sigma square by n, because we know that variance of t from equation number star is equal to mod of tau dash theta into gamma theta. Okay, so by using this equation, we can find out variance of x bar for our problem. So this is variance of x bar is tau dash theta, in place of tau dash theta what we have, mu dash. So if taking derivative mu with respect to mu, it becomes 1, and gamma theta is what in equation number 2. Now you can see here, in place of gamma theta what we have, sigma square by n. In this equation, sigma square by n, so multiply with sigma square by n, this is sigma square by n. So variance of x bar becomes sigma square by n. This is variance of x bar, and x bar is minimum variance bound estimator for mu. So this is the solution of this problem, and you can follow the same procedure for next problem, and you can apply the same concept and find out the solution. Okay, so come to the second problem, and second problem is a random sample x1, x2, xn is taken from a normal population with mean 0 and variance sigma square. Examine if summation of xi square upon n is a minimum variance bound estimator for sigma square. Okay, so this is our next problem, and come to the solution part. So in question we have x follow normal distribution, mean 0 and variance sigma square. So we can write the density function. Density function fx sigma square is equal to 1 upon sigma root 2 pi and exponential minus x square upon 2 sigma square, because mu is 0. Okay, and then likelihood function is defined as L is equal to joint density. Okay, then you can write fxi sigma square is equal to this quantity, and you can simplify it in form of this equation, 1 upon sigma root 2 pi whole power n, because we are multiplying n times. Okay, and do the same thing as I have mentioned in first problem, exponential n times product of exponential becomes exponential summation of the xi square. Okay, so after defining the likelihood function, we get this equation. Okay, now follow the same step as we have done in first problem. Taking log both sides, we get log of L is equal to, this is first function, this is second function. Okay, so log A into B, that means this is A and this quantity is B. Then you can simply write it log A. Okay, and log A, so this is power of n, then you can write in term of n log 1 upon sigma root 2 pi. Okay, and second quantity is exponential form, so log exponential is this thing, 1 upon sigma 2 sigma square summation of xi square. Is it clear? Okay, so now you can write first term in this form, and after writing this structure of first term, you can rewrite it minus or minus 1, it becomes minus n log sigma minus n log 2 pi by log property, and third term is 1 upon 2 sigma square summation of xi square. Is it clear? Okay, now then again readjust this expression, so we can write it log of L is equal to minus n by 2. Okay, log sigma square, just we are putting here square, that's why we are dividing by 2. Okay, and this is free from sigma square, so we are putting it k, just considering this term is equal to k, and last term is 1 upon 2 sigma square summation of xi square, so last term is this same here. Okay, now what is our next step? Next step is differentiating equation number 1 with respect to sigma square, and we get the resultant del log L by del sigma square is equal to, first term is n by 2 and log sigma square, differentiating with respect to sigma square, it becomes 1 upon sigma square. Is it clear? And second term is k is constant, so differentiation is 0, and last term 1 upon 2 sigma square summation of xi square, so summation of xy square is free from sigma square, just differentiating sigma square, so it becomes 1 upon sigma to power 4 minus sign 1 upon sigma to power 4. Then the final simplification of this equation is minus n upon 2 sigma square. Okay, plus minus minus plus, it becomes 1 upon 2 sigma की power 4 summation of xi square, and you can rewrite this expression by taking LCM 2 sigma to power 4 summation of xi square minus n sigma square, and just simply rewrite this expression in form of this expression, summation of xi square, just divide by n and minus sigma square upon 2 sigma to power 4 upon n. Is it clear? You can write this equation in form of this equation. So now our main objective to examine summation of xi square upon n is minimum variance bound estimator for sigma square. So we know that in Cramer Rao inequality, we have a standard form of first derivative of likelihood function. If this resultant is same as the standard form of the first derivative of likelihood function, as I have mentioned in my lecture for Cramer Rao inequality, then after comparison we can decide summation of xi square upon n is minimum variance bound estimator or not. Okay, so come to the next step. Okay, so we have, this is its standard form which I have mentioned in Cramer Rao inequality lecture, and our resultant for this problem is del log L by del sigma square is equal to summation xi square by n minus sigma square upon 2 sigma power 4 upon n. Okay, so now you can see here this equation number 1 is same as equation number star. Then we can conclude that sigma cap square is equal to summation of xi square upon n is an minimum variance minimum variance bound estimator, and the variance of sigma cap square is equal to 2 sigma power 4 upon n. You can find this thing as similar as first problem. Okay, so I think is it clear? So thank you so much. to everyone for watching me, and again we will meet with new lecture with new topic.